theorized in 1964 by Peter Higgs, Francois Englert, and Robert Brout, and later discovered in 2012 at the Large Hadron Collider, the Higgs boson is probably the most famous particle of the 21st century. But now that we have found this so-called God particle, why do we keep looking for it at the LHC? Well, the fact is, finding it was only just the beginning. The Higgs boson is a rather interesting particle as it mediates mass. This means it lets quarks, electrons, Z bosons, among other particles, to have mass via its interaction. It is kind of similar to how fundamental forces are mediated, but it isn't quite the same. But as a simple comparison, sort of just like how charged particles interact with the electromagnetic force, and therefore photons, so too does the Higgs interact with particles that have mass. Although that isn't really quite correct, it's more fair to say that particles that interact with the Higgs have mass. And the more they interact with the Higgs, the more massive they are. So it is through their interaction with the Higgs field, and therefore the Higgs boson, that they gain mass. So it is a little bit backwards. You don't gain charge by interacting with the electromagnetic force. But anyways, that's a little bit of an introduction to the strange and interestingness of the Higgs. But as of 2012, we know the Higgs exists. For a while, we weren't quite sure, we hadn't measured it, but now we know the Higgs has a mass of 125.11 plus or minus 0.11 GeV, has no charge, has a spin of 0, and among many other features. So, since we know about it and we know its properties, so why do we keep looking for it? And why do we keep examining it? Well, the thing is, we can kind of boil this down to three things. First and foremost, as mentioned previously, the Higgs interacts with massive particles. And since the Higgs is not very stable, it usually decays, we can look at how it decays to see how it interacts with these massive particles. See, particle interactions aren't always a 1 + 1 = 2 situation. It is more like when two particles collide or a particle decays into multiple particles, that processes is probability based. And so those that occur more frequently are usually ones that involve interactions. For example, we should expect from the Higgs, it should decay more frequently into massive particles because they interact with it more. Very basic. This could be a more detailed explanation, but this is not what this video is for. So if you think that's neat, subscribe. I think I'll probably make a video on that later down the line. So since the Higgs is more likely to interact with massive particles, we should expect our creation of Higgs to have a similar form. In fact, we have multiple graphs that have been produced essentially predicting how much each massive particle should interact with the Higgs. But the thing is, we haven't measured all of those. Sure, we have measured the Higgs interaction with bottom quarks, we've measured its interaction with the Z and the W, among other things. But for example, Higgs to 2 muon, we don't quite have a full measurement of that. We've been looking at it, we're close, but we do not have an error small enough for us to justify that as a discovery measurement. I actually worked on a Higgs to 2 muon analysis. There was a paper that came out last year? Yeah, actually about a year ago, about examining it from data from ATLAS, from Run 2 and Run 3. But anyways, a lot of other things also haven't been measured. Higgs to 2 gluon we should expect, and we don't have a measurement for. Higgs to an electron and anti-electron we should have, among many other things. So we want to get those measurements because let's say the Higgs doesn't actually couple to the electron quite as much as we would expect. That could be huge news. That could be really interesting and maybe lead us to new physics, because although we know about the Higgs and we have measured the Higgs and we have an expectation of how it should interact with matter, we don't have the measurements to match to our theory, essentially, right? We have a theory behind the Higgs, but we need to test said theory And so we need to examine the Higgs more than we already have to see if our theory is correct. We do this with a bunch of things. We still look at Z bosons and W bosons because more precise measurements allows us to check our theory to a finer detail, and perhaps small deviations could indicate new physics beyond the standard model. And speaking of new physics, that brings us to a second reason why we are interested in the Higgs boson still, and that is new physics. There are theories where different particles that we have never observed interact with the Higgs boson, or perhaps there are other Higgs bosons, other particles that interact with the Higgs field or mediate the Higgs field, and these might be charged. There's concepts of a Higgs boson that has 1 electric charge, 2 electric charge. There's a myriad of things, so we want to examine the Higgs to essentially see if some of these theories might be true, because by looking at the Higgs boson, it can potentially be a gateway into this sort of physics. So another reason why we're interested is new physics. And the third reason why we're interested in examining the Higgs boson is purely the fact that we don't have good measurements. We don't, right? We have a measurement of 125.11 plus or minus 0.11 GeV. That might seem like a very small error, but when you keep in mind other particles, let's take the W boson, we have measured down as 80.3692 plus or minus 0.0013 GeV. That is a considerably smaller error than our measurement on the Higgs. So since we don't have great precision on the Higgs, better measurements allow us to potentially get a more precise measurement, and as we get greater precision, it'll allow us to make better experimental results, benefiting those previous topics, right? So it is useful for us to make sure that we understand the Higgs in fine detail, because if the Higgs is different than how we expect, new physics? Maybe? Who knows? So that's exciting. So yes, we did find the Higgs boson over 10 years ago. Wow, 10 years. There is still a lot for us to learn about it and learn from it. So much more to discover. So that's why we are still interested in the Higgs. And if you're interested in the Higgs, look into it. Learn about it. Stay curious. There is so much cool things going on in the world of particle physics, the world of physics in general. We're only a small corner of this giant map of all the sorts of physics that goes on in the universe. But that is why we care about the Higgs. You've made it to the end of the video. Thank you for watching. This was the special 100 subscriber video. I wanted to cover something that I have worked on, and seeing as this was something that I did a little bit of during my master's while working on the Higgs to 2 muon analysis using run 2 and run 3 data from the ATLAS experiment, this was kind of a fun middle ground. I would have liked to make this video longer, but I am going to CERN for a month to do physics stuff. So a heads up, long form videos for the next month and a bit might not be as frequent. The Wi-Fi isn't great in the apartment hotel that they've set me up in, and I might not have the time to edit and record videos. That being said, there is still lots of quantum mech content to come. There's going to probably be a lot more shorts for the next few months until I am reorganized and I have the time to put together some long form videos and edit them. Please share these with your friends. We are so close to 500. We are about halfway there, past 250 while I was recording this. Thank you so much, everyone, for liking, subscribing, and following. And if you like this content, like and subscribe. There's a lot of physics stuff that we talk about, kind of main focus on particle physics, but also my interviews where I bring in people who are involved in the science community overall. Mainly been physics focused, but we got a science communicator, we got someone who builds games for teaching about science, so I am broadening that field. Anyways, I'll see you in the next video. Stay curious. Have a good one.